Let's give an example of how traversal can help us solve one of these interesting graph problems. So we're going to try and solve the ST connectivity problem. That's the idea that we have a source vertex and a target vertex, and we want to know, does there exist a path between them? So somehow we're going to need to traverse this graph. And so what I'd like you to do now is try and come up with an algorithm for connected. And you might try and draw some inspiration from our tree traversals earlier. Okay. And then what I'm going to do in a moment is give you an algorithm that you're going to have to debug. So maybe come up with them, maybe one, maybe don't. Up to you. All right. So now I will give you one possible recursive algorithm. Okay. So what we could do is say, is S equal to T? If so, return true. The base case is that someone's trying to find out, is there a path from something to itself? That's yes. The answer should be true. Otherwise, what you'll do is that for every neighbor of S, that is everything that is connected to S, you will call connected v comma t. And if that's true for any neighbor, you should return true. Otherwise, we'll return false. So this is a recursive algorithm that feels a little bit like the depth-first traversals that we saw for our trees. So what's wrong with it? There's a bug. See if you can figure it out. Okay, the reason, oh, it's blue. Okay, now you can try and answer. So the reason is, the bug, if you try and walk through it, you'll see there's a recursive infinite loop that happens. So what happens is we say, is 0 connected to 7? Well, we first say, is 0 equal to 7? No, so let's call connected 1 comma 7, and then we'll return true if that is indeed the case. So we get connected 1 comma 7. We've got to evaluate this expression. Is 1 equal to 7? No, so let's call if connected 0 comma 7. So basically here, since 0 is a neighbor of 1, we're going to go back and we're going to end up just getting into an infinite loop. So the next question for you is, how do we fix this? And maybe this question, if you didn't do the other two, try and do this one. This one's a little more concrete. Okay. So one way to fix it is, let's add marks. So what we'll do is, every time we go make a call to connected S comma T, we're going to mark S. And then we're only going to traverse neighbors if they are unmarked. And what this does is it avoids multiple visits to the same node. So we mark a node and that says you can only visit it at most once. So let's see here a little demo of this algorithm for recursive, or for connectivity. So this is just literally what was on the slide, and this is a very typical approach. So we'll start by looking at S, and we say, is S, we'll mark it first, and then we'll say, is 0 equal to S? No, the answer is no, so we're not going to return anything. So now we're going to consider every neighbor of S, and we'll check if they're marked. So is 1 marked? No. So let's call it connected 1 comma 7. So now we get here, and from the perspective of this connected call, the value for S is 1. So is S equal to S? No. So then we look and we say, is 0 marked? Yes, it's already marked, so we already went there. So we don't want to go back, or we're just going to get into an infinite loop. And so now we'll say, is 2 marked? Well, we'll check whether or not 2 is connected to 7, and because it's not marked, as we see, it's not white. So I'm indicating marks by erasing the color. So at this point, since 2 is not marked, we're going to check 2's connectedness. Okay. Now to do this, we make a recursive call, and we say, is 2 equal to 7? No. And then we need to consider all of 2's neighbors. Is 1 marked? Yes. Look, it's blank. It's already had all the goodness sucked out of it. So then we're going to have to check 5. 5 is not marked, so we make a recursive call. The first thing that happens when we make the recursive call is we say, is 5 7? No. So we check 2 to see if it's marked. And this brings up an interesting question, which I didn't mention before. If we have many neighbors, how do we know which one to look at? Well, I'm going to assume we'll always look at the smallest numbered neighbor first, but in general, it doesn't really matter. It could be a totally random order, and everything would still work fine. So I will check, in this case, 2 to see if it's marked. The answer is yes. So then we're going to look at the next child, or neighbor, which is 4. So we check. That means we need to now call connected 4 comma 7, which means first saying, is 4 equal to 7? It is not. So we consider 1, the smallest neighbor of 4. That is already marked from a long time ago. So then we move on to 3, which is unmarked. 3 is not equal to 7. And at this point, since 4 is already marked, we get to this return false statement finally. So we've considered all unmarked neighbors of 3. And now we're going to return false. So we return false. Hooray. So now we're at 4. We have 3 neighbors to consider. We've already looked at 1. We've already looked at 3. And so now we ask ourselves, is 5 marked? Well, 5 is already marked. In fact, that's where we came from earlier. So since we have no more neighbors, I'm also going to return false. And in this case, I am 4. Hence the asterisk and the black box. Okay, we're back to 5. So we've explored everything over here. 2 was already marked. So now we need to check 6. So we go to 6. It is not marked. We say, is 6 equal to 7? No. 6 looks back at 5. Already marked, so don't go there. Then looks at 7. So we're going to check whether 7 is connected to 7. Well, finally we found our base case. The answer is yes, it is connected to itself. So it doesn't even bother checking to see if 6 is marked, because the first step is if s equals t, you return true. So here's my true. 6, very excited, just says, great, I'm done. I'm going to return that true. One of my neighbors is true. So guess what? I'm also true. So we get back to 5. Now at this point, 5 is not going to look at 8, because if 6 is connected, we immediately return true. We don't keep going. So we're going to return our true value. So now 2 is in charge, says, great, I got a true. Passes the true back up to 1. 1, we have now looked at our neighbor 2. It gave us true, so we'll return true. And now the source has true. And at the very top level, we return true, and we're done. The answer is true. So that is the ST connectivity problem as solved through recursion. And so in the next video, we'll talk a little more generally about this approach that we've just used.